Okay, hi again, class. We're gonna pick off where we left off. So we were trying to generalize how to, approximate the area underneath the curve of a function in general. So we did one example with the left and the right endpoints, and that was just going to be a special case of what we're doing. So we had a function. In our case, this was x squared on some interval a to b. A was 0 and b was 1 in our example. So what we need to do is, in general, let's think about this. We have our function defined on this interval a to b. Okay. And what we want to do is, say we want to use n rectangles. So we want to chop this entire interval up into pieces that are equally spaced out. So n equally spaced out things. Well, what is the length of this interval? The length of the interval is just this minus that. So it's just b minus a. So that'll give you the length of the interval. And then how do you chop it up into n equally distributed pieces? Well, you divide it by n. So this quantity here that we're going to call delta x, this is a capital delta, the Greek letter is capital delta. Read delta x, is how we say this. Delta x is going to be the width, so if we chop this up into equally spaced pieces, delta x is going to be the width of each of these. So that has width delta x, that has width delta x, and so on. So delta x is going to be b minus a, the length of your interval, divided by n, where n is the number of endpoints. The number of rectangles we're going to use. So this is length of interval. This is number of rectangles. Okay, this is number of rectangles we're going to use. And that will tell us what delta x is. Basically, this width that each little sub-interval is going to have. So in the example we did earlier, delta x was 1/4. Because our b was 1, our a was 0, so we get 1 up here, 1 minus 0, and our n was 4, so 1/4. Okay, so this delta x gives us, basically this is going to be the base. The base of each of our rectangles is going to have this width. So this is like that number 1/4 that kept reoccurring in our calculations that we could have just factored out. Now the next thing is, let me zoom in, basically make this bigger, is we had options here. So we have many different choices. So if we have A and we have B, right? And let's say we chop it up into equal pieces like this, then the function, actually let me draw the whole function out here. Sorry about that. Let's just draw all of this out. So let's draw all this out. So let's say this is A. Doesn't have to be negative, but in this case, this is negative, but it doesn't have to be. And then here's B. And then we're just looking at a piece of our function from A to B. So maybe our function looks like this. And so let's say we subdivided, this interval A to B into equally spaced out things. So here's one piece here, there's another piece there, another one, and there we go. So we have all of these little smaller subintervals that we're looking at. So one subinterval is, we're going to call A, we're going to call it x sub 0, and we're going to call B x sub n. And you'll see why in a second. Because if we look at this, the subintervals that we get will be this. They'll be x0 to what I'll call now x1, so I'll just call this point x1, this x2, x3, x4, and x5. And so we can see that this should be x6, I guess, in this case. In general, it's some value n, we don't know what it is, but in this particular example, it's 6. So we have subintervals x0 to x1, x1 to x2, and so on, x5 to x6. Okay? So these are the subintervals that we get. So this one, this one, this one, each of these, they're subintervals that we're looking at. And you know, my drawing skills aren't the best, but they should all be the same width and whatnot. And now the question is, you know, if we just zoom in, maybe let's say right here. Let's look at this one piece right here from x3 to x4. The function was doing this, right? I'll draw it in red just to be very clear. So we're looking at this piece of the function here. Okay, now the height of our rectangle, we can take the rectangle to be this high, which this would be the output of the function at x3. We could take it to be this high, which would be the output of the function at x4. Right, this is my input. When you stick it into the function, f of x3 will be the height. This is my input, f of x4 will be that. Or honestly, I can take any number in between these. So maybe I take this guy. So I take a random point in here. Let's call it x star. We'll put like a star, a little asterisk above it. Then the output of the function is this right here. So this is f of x star here. Okay? That height. So we have a lot of different options. Let me move this up. We have a lot of options. So in general, within our subintervals, we're going to pick some point x star within them. When we use the left endpoint, we're using the number on the left, the smaller number. So the left endpoint, we will pick x0, x1, x2, all the way up to x5. So it'd be like this one, this one, this one, this one, that one, x5, and then we stop. And then with the right endpoint, we're going to pick the bigger number. So between x0 and x1, we'll take x1. And then from x1 to x2, we'll take x2. So you pick the bigger number, x1, x2, x3, x4, all the way up to x6. That's in the case of the right endpoint. But in general, we pick some number x star out of these. And then this also, in a sense, has a numbering. So in this case, this would be like x3 star because it belongs to the interval from x3 to x4, if you want to say it like that. But we don't have to worry about the details on that too much. So the idea here is, let's see, do I need this? Maybe I still need this. So this is a definition that we need to know. So this is a definition. So the numbers x1 star, x2 star, and we could start at 0, 0, 1, it doesn't matter, it's kind of up to your taste, up to xn star. So these numbers that we picked, so either these are left endpoints, right endpoints, or like some arbitrary ones. We will also do the midpoint. We'll see an example where these will be the midpoint in a second. These numbers that we use though, these are called the sample points, because they're the points that we're kind of using to sample and to get our area, because they kind of stand out from all the other ones. Okay, so these are the sample points that we're using. Okay, now when we put all of this together, what do we get? We get what we saw in the very first example, is you just kind of add up these areas, right? We're going to add up the areas. So, for example, if we take, maybe I can redraw this in a nicer way. Since it's very cluttered. So yeah, in general, we have this guy. Let's just say it looks like this. Then, if this is some point, like let's say x2, for example, and this is the x3, then, and we take this sample point here, x2 star, then what did we say? We said the height of the function here, so this is going to be the height of the function at x2 star, whatever that is. You just stick this number into your function, and that tells you how high to go, or low if it's negative. We'll talk about what negative area means. That's to come in a little bit. So for now, we'll just stick to more intuitive notions. And what did we do? So we said that the width of the rectangle was just going to be this always. That width is delta x. So base length is delta x. And then the height of the triangle was going to be this. Sorry, not the triangle, the rectangle. We take this to be the height, whatever the value of the function is at that point, at the sample point. And then this is height of rectangle. So the base is delta x, the height is the value of the function at the sample point, and then so this is the area that we get. So then we could call this A2, for example, since it comes from the second sample point. This is just going to be delta x base times the height, or f of x sub 2 star. Okay. Then the star is there just to mean it's just some random point. But again, the ones that we normally will use are the left endpoint, the right endpoint, and we'll do the midpoint in a second. So what does this mean is, this means that the area using n rectangles, so we call it A sub n, area using n rectangles. Remember, if this was R sub n, it's using n rectangles with the right endpoint. L sub n would be using n rectangles with the left endpoint. But this is in general. So the area using n rectangles, that's what A sub n is. That's just going to be the sum of all of these areas, right? The first area, the second area, blah, 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 and so on. So it's just going to be f of x1 star times delta x, because this was x2 star, right? But now, we didn't look at x1 star, so f of x1 star times delta x, plus now this one, f of x2 star times delta x again. Again, the width or the base of the rectangle is always the same. Plus yada yada yada, so on, f of xn star times delta x. So this goes on for n more terms. Oh, and this should actually be x sub 0, I'm sorry. So the 0th sample point, the first one, and so on, all the way until we get to the very end. Okay, and so if we want to write this in a compact way, we can just factor out the delta x and multiply it by this sum right here. F of x sub 0 star and so on. So that's the general formula for the area. You know, in the most general form. This looks very confusing, and I understand there's a lot of like symbols and there's stars and all this stuff, but with a lot of practice, this notation will make a lot more sense. Trying to write things in general in math usually makes things look very confusing, but the whole process will hopefully make sense, and that's all that matters. Okay, so we have that. And actually, we want to even rewrite this in a more compact way, because this is going to be useful. And so this is going to lead us to talk about what's called sigma notation. So you may have learned this way back in the day, but it's good to relearn it or refresh yourself. So sigma notation is what we're going to talk about. And it's kind of a way of writing this thing in a very efficient way. So to start, we need to talk about sequences. So what is a sequence? So a sequence is a list of numbers. And sometimes it's random, or sometimes we kind of have like a formula for it that can tell us. For example, this guy here, 1 over 2 to the n. Okay, so 1 over 2 to the n is a sequence, but you know, what does this mean? This is basically just the list of the following numbers. What you do is, some people will allow you to include n is 0. In some cases you can do that, and in other cases you can't. In this case, n being 0 is fine. So all we're going to do is let n be 0 and see what this becomes. Well, if n is 0, you get 1 over 2 to the 0th. 2 to the 0th power is just 1. So you get 1 over 1, and this is just 1. So this was n equals 0. That's what happens when n was 0. Now, what happens when n is 1? Well, you get 1 over 2 to the first power, which is just 1/2. So 1/2. So this is when n is 1. N equals 1. And then if you let n be 2, you get 1/4, right? 1 over 2 squared. So 1/4. And you know, the list goes on. It can go on and on forever, if you'd like. It can really, yeah, it'll just go on forever. Okay? So this is what a sequence is. Now, what is a series? What is the difference between a sequence and a series? There's not much of a difference. A series is, what is a series? Series, as opposed to a sequence, a series is a sum of the terms in a sequence. So for example, if we get, let's say, the first 5 terms of this sequence and add them together. So we take 1, plus 1/2 plus 1/4 plus the next one would be what, 1/8, right? Because if you take 2 cubed, it's an eighth. And then 2 to the 4th plus 1/16. This is a series. It's just the sum of the terms of this sequence. Now this sum could go on forever, in which it's called an infinite series, or it could be a finite amount and it's called a finite series. But either way, that's all a series is. So what does any of this have to do with the sigma notation? Well, the sigma notation allows us to write this form of a sum in a much more compact way. So if we wanted to write this sum in a compact way, we would write it as this. So let me say that this equals a capital S. So capital S, actually, we're going to write it like this. The reason it's called sigma notation is because you use the Greek letter sigma, which some people can write very nicely and amazingly, but I cannot. So this is as good as I can do. You write this. This is the Greek letter sigma. It's capital sigma. Maybe leave a little bit of space, because I'm going to write something here and here. So this is sigma. And I'm going to write n, or maybe I is better. Sure, I equals 0 to 4 here. So what does this mean? So I equals 0 down here, and then 4 up there. Interesting, okay? And then I'm going to write 1/2 to the n, okay? This means the same thing as all of this. Because what does it mean? It means, now, oh, this should be an I, sorry about that. So this means let I be a number from 0 and then 1 and then 2, 3, all the way up to 4. So we're going to increment I starting at 0. So you start at 0 and then 1 and then 2 and then 3 and then 4. And then let I, go into this position and just add up the value you get. So essentially, right, we're looking at the sequence that we construct. This says make the sequence of the first 5 terms here. So the sequence we've already seen would just be 1, 1/2, 1/4, 1/8, and 1/16, right? This is when I is 0, when I is 1, when I is 2, 3, and 4. These are the numbers we get. And it just says add all of these up. So just add these guys up. So this literally means you take 1/2 to the 0th plus 1/2 to the 1st. Which is exactly what we have down here once we simplify. So that's all sigma notation is. It's just a very compact way of writing out the terms in a sum. So if we now go back to what we had, we go back to the formula for the area. Maybe I should erase this as well. So the area formula was this. In general, for n rectangles, the area was this. It was delta x, since the width would never change. And then it was just okay. So now, if we think about it, we have a sequence that we can get out of this. The sequence is just this. It's f of x sub 0 star, f of x1 star, all the way up to f of xn star. I'm sorry. You have to put the little squiggly brackets here. These terms constitute a sequence. And look what we're doing. We're adding the terms in the sequence all together. So this is actually a series. This is the series of this guy. So really we can rewrite an the same way using the sigma notation. We have delta x now multiplying the sum here. So where do we start? We start from 0, right? 0, 1, 2. From 0 to n being the number of rectangles of f of f x I star. Right? I is 0, we get this. I is 1, we get that. I is 2, we get 2, and then n all the way up to n. So these two are equal. And you can see this is a much nicer way of writing all of this. It's much more compact. So this is what we're going to start using instead. And we'll see that this has a big advantage as well. Okay. So then the idea was this, remember, is we have this an. And the idea was this. So this becomes now the definition. The area under a curve f of x from A to B, or I should say on instead, is this. Right? So if you start taking an infinite amount of rectangles, so you just take a bunch of rectangles and let the number tend to infinity, we should get the perfect right answer. So we saw how it worked out for the case where an was the right endpoint, so r sub n. L sub n also works, but in general, for any area that we get using any set of sample points, this should work out. Okay, and this is kind of some of the technical stuff. Maybe you don't have to worry about it too much, but it has to be said at least once. Okay, so now let's do a new type of sampling. We're going to use the midpoint as our sample. So, new sample point method. Midpoints. So we're going to use the midpoints of each subinterval in this case. And let's look at the function, let's look at the function f of x is x cubed on this interval from 1 to 3. Okay, so let's graph this real quick. So here's 1, and then here's 3, and then the value of, if you stick 1 into the function here, you get 1. So at 1 we're down at 1, and then at 3 we're all the way at 27. So this function is a very rapidly increasing function. So we're just going to look at this piece of it here. Just looking at this piece of it here. So from 1 to 3. And maybe this should be black instead. Okay, so it's rapidly increasing to 27. And then we're going to stick with the 4 sample points. So we're going to use 4 rectangles, so we get 4 sample points. So n equals 4 rectangles. Okay. So how do we figure out what delta x is? So remember, delta x was b minus a, so 3 minus 1 over 4, which gives 1/2. So the width of each of our subintervals is going to be 1/2, which is good because it's, not too big, not too small. We can visualize it well. So that's going to mean that each of these guys is a half. So if I'm at 1 and I need an interval to be of length 1/2, I need to go a half unit to the right, correct? So this will land me at 1.5. And then if I go another half increment, then I'm going to get to 2. And then another half increment to 2.5. And then from 2.5 to 3. So notice that if I just take delta x and I add it a bunch of times to the very first point, you will essentially get to where you need to be. So 1 plus delta x is 1.5. And then 1.5 plus delta x is 2. And then 2 plus delta x is 2.5, and then another delta x is 3. So this gives us the subintervals as well. The subintervals are, you can easily generate them once you know delta x. You just take the farthest left point and just keep adding delta x. So the subintervals are these: 1 to 1.5, 1.5 to 2, 2 to 2.5, and 2.5 to 3. So these are 4 subintervals. Okay? And then now, normally we either were going to take the left endpoints, right? We either took 1, 1.5, 2, and 2.5, or we took the right endpoints, which were this one, 2.5, and 3. But instead, we're going to do something new. We're going to take the midpoint of each of these guys. So the point in the middle, and that's where the star comes in, the x of I star, because the star is kind of means an arbitrary sample point, because it could have been any point between 1 and 1.5, or 1.5 and 2. And in this case, we're going to take the midpoint. Okay? So what is the midpoint of these two? Well, it's 1.25, correct? If you want a general way to get that, right? If you want to get to not, remember we went from here to here by adding the whole delta x, but to get to half of it, you would add half of delta x. So half of 1/2 is a fourth, or 0.25. So if you take 1 and you add it to 0.25, you get to the midpoint, 1.25. And then again, if you take a fourth, or 0.25, and add it to this, you get 1.75. And then similarly, when you do it here, you get 2.25, and then 2.75. So these are the guys we're going to use, and maybe, yeah, that's fine. So these are the sample points that we're going to use. So this is like x sub 0 star. Maybe this is better. This is like x sub 1 star, x sub 2 star, and then x sub 3 star. Okay, so this is what the star means. It's just these are the sample points that we're going to use. Now the midpoint. Okay, and then what do? Based off these sample points, we get heights of the rectangle, right? Because the output of the function at each of these points tells us how large our rectangle should be. So now we're going to take 1.25 and cube that essentially. So that's going to give us, I don't know if we can do a full fraction or maybe not. Maybe just deal with, so maybe I'll just leave it like this. Instead of finding out the actual number, we'll just say that this right here, that is f of x sub 0 star. Which, 1.25 really is 5 divided by 4, right? So it's really 5 over 4 cubed. So that number, is going to be, this is kind of nasty to write as a fraction, so we'll just leave it that way. But what you're essentially doing is you're taking this number and cubing it. That tells you how high to go. But we're just going to leave it in this arbitrary, general form. So this is f of x sub 0 star. Then when you cube 1.25, you get this height here. So that's f of x sub 1 star. And then again, you take 2.25 and you cube it. That's f of x sub 2 star. Then last but not least, take this guy and you cube it, and that's f of x sub 3 star. Okay? So these are now the heights that we're going to do. And so how do our rectangles look? So for this width here, we have that height. So the width again is still a half. So 1 to 1.5, that's a half. But the height that we used was the output determined by what happened when we stick this number into our function. So with the left endpoint, we would have stuck this into x cubed. With the right endpoint, we would have stuck that into x cubed to determine the height. But now we're just sticking in 1.25. And then the same thing here. So now the height is this, and the width is the same. I'll get rid of this here. Maybe just for clarity, we can get rid of this now. But still leaving these maybe to see that, yeah, this is really the midpoint that we're using. And then here, we have that. And last but not least, this is the height for that width that we want. Okay, so the midpoint looks like a pretty good approximation. I mean, if you think about it, the only spots that we're kind of missing are like this one here, this little spot, this one, and that one. So it looks pretty good. It doesn't seem bad whatsoever. And let's actually calculate what this will end up being. And also a small note, I guess, also to help you with your calculations, is remember that this was 1.25, right? If you add now delta x to this, the width of the interval, right, you're going to go from here to another width of the interval. It'll jump you to your next sample point very easily. So if you just take this and you add delta x, this is going to give you what you needed, the 1.75 that we needed. And then to this now, this next point here is if you add again the width of the interval, a delta x, that's again going to give you 2.25, which you needed. And so once you have one point, you can get the rest of the sample points very easily by just using delta x. Same way that we constructed the subintervals, right? Once we had this point 1, all we had to do was keep adding delta x to get the next points in the subintervals. So delta x is extremely useful and for many, many reasons. So this is kind of nice here too. Okay, and then now let's maybe use our fancy sigma notation. So the area, but first let's write it in general. So the area a sub 4, well, in this case, because we use midpoints, we'll use m. M means the midpoint with the midpoint method. That's going to be, right, what's the width of this is a half. So 1/2 times, what's the height of this? Well, it's 1.25 cubed, right? And then to that, that's the area of this guy. And then again, what's the width of this rectangle? Again, it's a half. And then you multiply that by now, what? 1.75 cubed, because that's how high we went up. And then a half times again 2.25 cubed, and then plus a half times 2.75 cubed. Okay, that's what the sum is. You know, that's just the area of these four rectangles added together. Okay, and then we can see that again, using algebra, we can just pull this 1/2 out because it's a common factor in everything. And this is just 1.25 cubed plus 1.75 cubed plus 2.25 cubed and then notice this is exactly what we were writing in general, like at the beginning of the lecture. This is f of x sub 0 star, right? Our function is x cubed, so when you stick this number, x sub 0, into the function, you're cubing it. This is f of x sub 1 star. So hopefully this is looking very similar to what we saw. Again, like I said, when you try and generalize math, it looks really confusing, but hopefully this is not too bad. And right, this is our delta x that we had. So it's just delta x times the sum of the outputs in each of these sample points that we're using. And then instead of writing this out, we can use sigma notation and write this as 1/2 the delta x times the sum. Okay, where do we start? We started at 0. So I equals 0. And we went from 0, 1. This is f of x sub 2 star. And this is f of x sub 3 star, all the way to 3. So you start from 0 to 3. And then this is f of x sub I star. So all of these are the same. So see, this is just a compact way of writing out all of this. But when you do all of this, when the dust clears, we end up getting that the answer is 19.75. 19.75 is the approximate area under the curve. Using the midpoint. Using midpoints as samples. So the midpoints were these sample points in this case. Okay, not bad. So again, if you use that little cheat that we had where you can use the antiderivative and whatnot, the actual answer is 20. So you can see that this got really close with just 4 rectangles. Very, very close with just 4 rectangles. And so if we, used an infinite amount of rectangles, but maybe like even 8 or 16, this would get very, 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 very close. So we would be pretty dead on. And this is actually how this kind of stuff works in real life, because many things in real life you can't take as antiderivative, so you have to approximate it. And there's whole fields of research dedicated to finding approximate values of integrals and stuff. So this is a very big field, and if people spend that much time doing it, it has to be important, right? Maybe not, but hopefully later in the course we'll see why it is important. And now the other thing that we can talk about is, again, to draw a parallel to derivatives and things like that. Is what does the area under the curve tell you, like physically, for example? So let's think about this. So velocity, remember, velocity was the derivative of position. So remember, velocity was the derivative of position, i.e. if x of t, remember this means time, and x is kind of like how far horizontally you are from an origin. So let's say, like, you know, you have some guy in a race, and this is the origin, and then this would be x of 0. So at time 0, he's 0 meters away from the origin. And then maybe he progresses a little bit. Now he's in his like sprint stance, doing his thing. Now this is like x of 1, so 1 second later. So 1 second later, let's say maybe he's at 5 meters from the origin. And then next thing you know, he's like really putting that work in, and now he's here, and then this is like x of 4. So 4 seconds later, he's, let's say, at 70 meters. So that's what x of t represents. It was the position of some object, doesn't have to be a person, just some object with respect to the origin. And if it's negative, it means you're to the left of the origin, but he's only to the right, so positive. So this was the position, the function that gave you position. And you know, you could actually graph this thing. If you graphed his position, for example, let's say it looks something like this. So this would be x of t. The position as a function of time. And these units were in meters, right? This was meters, the units, and this was in seconds. Now, if you take the derivative, so if you took any point t, let's stick to our traditional thing that we're doing now. If you take t star, some random point, and find, and you know, look at the tangent line, the slope of this tangent line would tell you the velocity of the guy or the girl at that instant of time. So that's what x prime was. X prime, which gives you the slope of the tangent line, which we can call v for velocity. This is the velocity. But it is the derivative of the position of the object. And remember, this would just tell you the slope of these lines, the lines that we can construct. So the slope of this line, the slope of that line, any of these slopes. That's what the derivative tells you. And then what would the units of this be? So let's think about what the units are. So units here are meters. The output units are meters. But these values are slopes, right? And if you think about in general what a slope is, it's a change in your y coordinates divided by the change in your x coordinates, right? It's delta y over delta x, which in this case, y is x and x is t. So maybe it's a little confusing, but right, our outputs are x and our inputs are t. But it's just, you know, a division of the units of the output divided by a division of the units of the input. So the units of this guy, because it's a slope, these are meters per second. It's a velocity, makes sense, right? Meters per second. Okay. So Now let's say you have, instead of being given the graph of the position, you're given the graph of the velocity of the person. So you have v of t, and then you have t here. And let's say it looks something like this. This might be realistic because, right, the guy has no velocity at the beginning, and then they start to speed up and they get really, really fast. They hit some peak velocity, and then it starts getting less and less, and then this is where they stop running. You know, they pass the finish line and then they fully decelerated to this point. So this seems like you know, a reasonable velocity curve for a runner doing maybe like a 100-meter dash or something like that. Now we said the units here are meters per second, and this is seconds still. So the area under the curve here, first off, what does this area give you? This area is the total distance ran. So the area underneath the curve is telling you things about the position, which makes sense, right? Because we said the area under the curve relates to the antiderivative. So it undoes velocity, so it should tell you about the position. And actually it tells you the amount of distance that the runner ran between t equals 0 seconds and, you know, whenever they stop. So this is the total distance that the runner has ran. And so what are the units? Well, the units are just meters, right? So the units are in meters. So notice again, this is undoing everything the derivative did. The derivative took us from meters to meters per second. The area under the curve, or the integral, or the antiderivative, is taking us back to meters. And last but not least, is it kind of makes sense why it should give us meters, right? Because this, we approximated this with a bunch of rectangles. Well, if you think about the rectangle, what is the unit on the x-axis? Because, right, that's a delta x. If we take some delta x here, we take a delta x, the unit of delta x is in seconds. So this is in seconds. And remember, we invariably took some sample point. Let's just say we take the left endpoint, so this, to get this little rectangle area. Well, the height here is in meters, right? So let's just say this is f of x sub star. This is in meters. So what happens when you multiply, this unit is in meters per second. So what happens when we multiply these? You're taking meters per second and multiplying it, so that's the output, the height, and you're multiplying it by the base, seconds. Well, the seconds just cancel out and you get meters. Just m, because I'm out of space, sorry. So notice that's like another reason why it's kind of undoing it. It's because this whole rectangle procedure. So again, you're kind of seeing all of these ideas really coming together, and they have a lot of applications in real life scenarios, like in probability and statistics, which I mean a lot of fields use, and physics and engineering. These concepts are very, very essential. And so this is kind of a nice taste of what's going on with the interplay of the derivative and the antiderivative, and you can see why all of this is kind of bunched into just one calculus course. Okay, so I think we can conclude this one for now, and we can start on the next section in the next video.